All right, so Liv Naamoten's nuclear reactor project, huh? Pretty ambitious stuff. We're talking megawatts of power. But no steam generators, no turbines. Sounds wild, right?
Definitely a different approach. Direct conversion technology. They're aiming to just, well, convert the heat straight into electricity.
Yeah, make the whole system smaller, more efficient, even safer, potentially. But I gotta say, it sounds a little too good to be true. Like, how do they actually pull off this direct conversion?
Well, there are two main technologies they're focusing on. HLEC, that's heat to light to electricity conversion, and then TPV, or thermophotovoltaic conversion.
So instead of the whole boiling water thing, they're going heat to light and then straight to electricity.
Exactly. Both those methods, HLEC and TPV, they basically convert heat energy into light first, then that light gets used to generate the electricity. It's kind of like imagine a super efficient solar panel, but powered by heat, not sunlight.
Okay, that's a pretty cool image. But come on, finding materials that can handle a nuclear reactor, that's got to be a nightmare.
Yeah. Oh, absolutely. That's one of the biggest challenges. I mean, we're talking over 1,000 degrees Celsius, constant radiation bombardment.
Intense. So, like, the right materials are make or break for this whole thing.
Absolutely. If they can't find materials that can handle the heat and the radiation, the entire concept falls apart.
So what are they looking at? What kind of materials could even stand a chance in there?
They're exploring a bunch of cutting-edge options, advanced ceramics, metamaterials, even nanomaterials.
Nanomaterials, like those tiny things, smaller than a human hair? What makes them so special?
Well, they've got these unique properties. They can be incredibly strong, resistant to heat, and they handle radiation damage really well. Plus, you can engineer them to have specific optical properties.
Optical properties. So, like, they're designing the reactor atom by atom with these nanomaterials.
In a way, yeah. And it's not just nanomaterials. They're also looking at quantum dots, tiny semiconductor nanocrystals,
Quantum dots in a nuclear reactor? Sounds like science fiction.
Yeah, but it could be key. See, these quantum dots, they can absorb light and then re-emit it at a different wavelength. So they could actually fine-tune the light spectrum inside the reactor, make the energy conversion even more efficient.
Wow. All right. So with these crazy materials, what does the reactor design actually look like?
Okay, so picture this. A gaseous heat absorption blanket surrounding the reactor core. It could be a mix of special gases, potentially even containing, get this, nanoparticles.
So it's like a glowing gas converting heat into light.
Exactly. A three-dimensional omnidirectional light source right there in the reactor. And then that light gets captured by specialized photovoltaic cells that convert it into electricity.
A gaseous light-emitting panel. Man, that is wild. But even with all that, managing the heat from a nuclear reactor, that can't be easy.
You're right. Thermal management is crucial. They're looking into some pretty advanced stuff, microfluidic or aerosol-based thermal control systems right inside the reactor.
So like tiny little pipes and valves controlling the heat.
Kind of. It would act like a super precise heat exchanger. They could fine-tune the temperature and optimize the energy flow really well.
Okay, but it doesn't stop there, right? We got to talk about photon recycling. What even is that?
So when you convert heat to light, not every single photon gets converted into electricity right away. Some get lost, absorbed.
I see. So photon recycling is about catching those escapees.
Exactly. You redirect them back to the photovoltaic cells, give them another chance to be converted, squeeze every last bit of energy out of the system.
Okay, that makes sense. But honestly, is all of this even feasible? It's got to be incredibly complex, and the cost.
It's definitely a high-risk, high-reward project. That's why they've broken it down into 3 phases. The first one, a feasibility study, will figure out if this whole thing is scientifically and economically viable.
Smart. Got to make sure it has legs before going all in. All right, So what about those later phases? What happens if they get the green light?
So if the feasibility study checks out, they move to phase 2, building a lab-scale prototype of the whole DCT system.
So a mini version of this crazy reactor.
Yep. Scaled down, but with all the key elements. The gaseous blanket, the photovoltaic cells, the works.
All right, so that's where the rubber meets the road. They'll actually see if this thing can generate electricity.
Exactly. And if that prototype works. Phase 3, designing a conceptual small modular reactor, an SMR, using DCT, and then figuring out how to commercialize this whole revolutionary technology.
Wow. From a lab experiment to a potential power plant. Okay, we need to dig into those phases and the challenges after. Well, we don't have breaks here. But before we get to that, tell me about the people behind all this. Who are these visionaries trying to change the world?
Well, Dr. Lev Naamoten himself is leading the U.S. side. He's not just the brains behind the project. He actually founded N5 Digital, the company developing this DCT tech.
So he's really all in on this. What about the team in Israel?
They're led by Dr. Ezra Elias from Technion. It's a pretty famous institution for tech innovation. He's bringing a lot of experience to the table.
A real power duo. It sounds like they've got a top-notch team to tackle this challenge. But let's be real here. This is ambitious, to say the least. What are the chances this actually works?
Honestly, it's a long shot. This is so different from how we do nuclear now. There are going to be so many unknowns, roadblocks along the way.
But hey, sometimes those long shots are the ones that change the world, right?
You're absolutely right. That's what makes this project so captivating. It's not just about, making things a little better. It's about pushing the boundaries, maybe even revolutionizing a whole industry.
It's a moonshot for sure. But even if they don't hit every single goal, the knowledge they gain from this research, that could be huge, right?
Absolutely. Think about it. If they can make even a little progress on materials that can survive inside a reactor, that's a breakthrough.
Yeah, good point. And those material science advances could have applications way beyond nuclear energy.
Exactly. That's why I'm optimistic about this project, even with all the challenges. Even if DCT doesn't become the main way we do nuclear, the research, the development, it could impact other fields too.
It's like planting a seed. Might not go into a giant tree, but it could still change the whole landscape.
I love that analogy. It really highlights why supporting ambitious research, even when it seems kind of crazy, is so important. You just never know what might come out of it.
Okay, so we've talked about the science, the impact.
Yeah.
But let's get practical for a second. How are they planning to fund this thing? Developing tech like this can't be cheap.
Yeah, you're right. It's going to be expensive. Their proposal outlines a budget of $50 million over the 3 phases.
$50 million. Where are they going to get that kind of money?
They're looking everywhere.
Yeah.
Government grants, agencies like the Department of Energy, the National Science Foundation.
So tapping into that clean energy research funding makes sense.
Yeah.
What else?
They're also looking at Israeli research grants, international collaborations, even private investment, reaching out to venture capitalists, the ones who specialize in clean energy and, futuristic tech.
Casting a wide net. Smart. It shows they're serious about making this happen.
It does. The fact that they're getting interest from so many different investors, that says a lot about the potential here.
It's encouraging to see people taking a chance on something this bold. But let's shift gears a bit and dive into those 3 phases you mentioned earlier.
Sure. So phase 1, the feasibility study, that's where they figure out if DCT is even scientifically possible. Lots of modeling, simulating how the system behaves under different conditions.
So proving it on paper before they build anything.
Exactly. And they'll be testing materials too, seeing how they hold up under those crazy temperatures and radiation. This is where those nanomaterials and quantum dots, really get put to the test.
Sounds like a critical first step. What about phase 2? What happens if the study gives them the thumbs up?
Phase 2 is where it gets real. They go from theory to practice, start building a lab-scale prototype.
Well, a mini version of this revolutionary reactor.
Yes, a scaled-down version, of course, but with all the key parts. The gaseous blanket, the specialized photovoltaic cells.
This is where it all comes together. They can finally see if their theories actually work.
Exactly. And it won't be easy. Building a working prototype, that means overcoming a whole new set of engineering challenges. Advanced cooling systems, integrating all the different parts seamlessly.
Sounds incredibly complex. But if they can pull it off, that would be a huge step. So what about the final phase? What happens then?
Phase 3 is all about scaling up, making this thing commercially viable. If the prototype works, they start designing a conceptual small modular reactor, or SMR, that uses DCT. And then figuring out how to actually bring it to market, finding partners, getting more funding.
From a lab experiment to a potential power plant. That's quite a journey. But let's zoom out for a second and talk big picture here.
All right, what do you have in mind?
Well, we've talked a lot about the technical stuff, but what about the impact on energy as a whole? If this actually works, what could DCT mean for the world?
That's a great question. If they can actually make DCT work, it could totally change how we generate and use energy. Imagine nuclear power without those huge power plants. Smaller, more modular reactors deployed almost anywhere.
So instead of a few giant power plants, we could have a whole network of smaller ones, maybe even powering individual communities or industries.
Exactly. And that could make our energy grid so much more resilient, less vulnerable to problems. Plus, think about bringing clean energy to remote areas, places that don't have reliable power now.
That's a pretty compelling vision. But, let's not get ahead of ourselves. This is still a long shot. Lots of hurdles to clear before DCT becomes, the standard.
You're right. But that's what makes it so exciting. It's a bold idea, and it could really make a difference. And even if it doesn't fully succeed, the stuff they learn along the way, the innovations that could lead to other breakthroughs down the line.
It's a good reminder that sometimes it's not about the destination, it's about the journey, the discoveries you make along the way.
I like that. That's a great way to put it.
Okay, so I think it's time to wrap up our deep dive into Lev Motin's DCT project. It's been fascinating exploring this cutting-edge science and the potential it holds.
It has been a pleasure.
We've talked about some mind-blowing science, the engineering challenges, and how this tech could change the future of energy.
It really shows what's possible when brilliant people come together with a shared vision, even if it seems a little crazy at first.
So to everyone listening, keep exploring, keep asking questions, and don't be afraid to chase those big, seemingly impossible dreams.
Sometimes the most revolutionary ideas are the ones that sound the craziest.
Thanks for joining us on the Deep Dive. Until next time, stay curious. So we've talked a lot about how amazing this DCT project could be, revolutionizing nuclear power and all. But what about the real world challenges? Building this thing can't be a walk in the park.
Yeah, no, for sure. There are some serious hurdles to overcome before this goes from a cool idea to an actual working reactor.
Like what? What are some of the biggest obstacles they're facing?
Well, the materials science, for one, it's pushing the limits of what we can do right now.
Right, the extreme temperatures, the radiation. Finding materials that can handle that is a tall order.
It is. They're looking at some cutting-edge stuff like ceramics, metamaterials, even nanomaterials. But each one has its own problems.
Can you give me an example?
Sure. Ceramics, they're good with high temperatures, but they can be brittle, and under constant radiation, they could crack.
So it's not just handling the heat. It's got to be durable enough to last for years in that environment.
Exactly. And then you've got metamaterials, engineered to have properties you don't find naturally. They're great for manipulating heat and light, but making them on a large scale, that's still really difficult.
It sounds like a balancing act, pushing the boundaries of material science, but also making it practical, affordable.
It is. And that's just the materials. You've got thermal management, photon recycling, integrating all these complex components.
Right.
It's a lot.
We talked about those fancy cooling systems, redirecting the photons.
Yeah.
Yeah, that sounds like a logistical nightmare.
Yeah, it's going to be tough. They need super precise control systems to manage the heat flow, keep everything running smoothly within tight tolerances.
So it's not just building it, it's building it so it runs reliably, safely for a long time.
Exactly. And then there's a question of scale.
Right. Even if they get a prototype working in the lab, making a full-scale, commercially viable reactor, that's another beast entirely.
Yeah, scaling up any technology is tough, but a nuclear reactor, that's a whole other level.
So they might have to make compromises along the way. Maybe sacrifice some efficiency or performance to make it more practical, easier to manufacture.
It's possible. But, I think that's part of what makes this project so exciting. They're taking risks, pushing the limits of what we think is possible.
It's like it reminds you that real innovation, you got to embrace uncertainty, even the chance of failure.
Absolutely.
Yeah.
Even if this specific project doesn't totally work out, what they learn, the innovations, that could lead to other breakthroughs down the line.
It's like planting a seed. Might not grow into a giant tree, but it could still, make the soil richer, help other plants grow around it.
That's a great way to think about it. And it shows why it's so important to support this kind of research, the ambitious, forward-thinking stuff, even when the outcome isn't guaranteed.
Well said. Well, I think it's time to wrap up our deep dive into Lev Motin's DCT reactor. It's been a wild ride exploring all this cutting-edge science and the potential it holds.
It really has.
We've seen that even the most ambitious ideas, the ones that seem kind of crazy at first, they can take root and start to grow when you've got brilliant minds working together.
And who knows what amazing things might come out of it.
So to everyone listening, keep exploring, keep questioning, don't be afraid to chase those big, seemingly impossible dreams.
Because sometimes those are the ones that change the world.
Thanks for joining us on the Deep Dive. Until next time, stay curious.